Hey, thanks guys for coming in. I think we've been having like some couple of good sessions going on. We want to keep up the momentum too. We are getting some external speakers to talk about deep learning and automation this month and next month. We'll publish it soon. Who's going to come in. So this session specifically is going to be on image classification using Keras, deep learning, right? I've given this talk in a couple of places already, so if you search my name on YouTube, you're going to see this talk. So if I don't do well here, probably you have a reference where I've done well, right? So you can go and look at that video. Okay.
So then that would be an actual skill test.
Yeah, you got the pizza, right? So, alright. So, the way, again, this session is going to be very hands-on. That's the way most of my sessions will be. I sent notes out saying that you need to install certain packages before coming here. So, if you want to just listen in, that's fine. But if you want to follow along with the code, that's cool too. You can execute it as I'm executing through it. The code for it is available in my GitHub, so the link will be shared after the talk, or just go to github.com and /Malaikannan, that's my handle. You can get this code from there, Python from there. So
I have John, Sid, Julius, Vimal, Amol, and I.
okay.
So we have the Gilead team on the call as well, right? And I'm projecting the screen.
Sure. Thanks, Amir. Thanks for joining. Yeah, thanks for joining.
Okay.
Okay. So,
Alright.
yeah, I know there are a lot of deep learning frameworks that are out there, right? There's TensorFlow. There used to be Theano. They just said like they don't want to support it anymore. So it's one of those grand old daddies of deep learning frameworks. PyTorch, Caffe, there's a lot of frameworks for there. My favorite is Keras. Since I'm very closely associated with the community. We in fact like started a community around it. There were like five of us. We started the community around Keras. 7 of us started the community around Keras. I think way back in 2015, late 2015. So we had like we started the Slack channel and all those things. So I'm very close to my heart since I was through it, like and even for the previous startup what I ran, I hired a lot of folks from Keras open source community. It's been like pretty good for me. Okay, so it's a deep learning library. Works on top of TensorFlow, Theano. It works on top of CNTK now. That's a Microsoft deep learning framework. The reason why I prefer Keras is it helps you to prototype things very, very fast, right? You can sit and write your own code, like, if you're good enough, you can actually write a C++ CUDA version of it and port it over to a GPU for execution and whatnot. Yes, you can do that, or you can use Keras where you can like quickly prototype it and see whether this approach works or not, and then like go to the next one. Okay? So that's a really big advantage of actually using Keras. So the documentation for Keras is available in keras.io. Francois Cholet, he writes really good documentation and the community contributes to it too. There's a Slack channel for Keras, so if you're not there, probably I suggest you to join. It's going to be good. There's a Gitter channel too for Keras, but Gitter, not a lot of key contributors are contributing back, so that's what I've seen so far. I don't know whether that has changed recently. So, yeah, there's a Gitter channel too if you want to search. So what we're going to do today is image classification using deep learning, right, on Keras. So we're going to take the hello world of image classification, the MNIST data set, which is handwritten data set. We're going to take that and build a model, right, couple of models. One, we're going to use a feedforward neural network. The example what I gave in the previous session, that's the classic feedforward neural network. And then we're going to build like another model for convolution neural nets. I'll show the different why we need convolution neural nets. If you look at like a lot of new applications that are coming up on image processing field, like or image classification, that is all convolution neural nets related. That's the more that's what it works since we make an inherent assumption that we're working with volume, right? So convolution operation. So that is the thing. The other reason is the data set is you don't need to do a lot of pre-processing. It's already normalized, it's centered and all those things. So it is good from that perspective. And the data set is small enough to be trained on a CPU. So you don't need to worry about having a GPU for training this model. So you can actually train it and you can see the output right there. And again, it's a hello world for image processing. right? Whenever you write a code, you start with hello world. So that's the reason. A couple of citations. For this tutorial, I'm referring content from Andrew Karpathy's Stanford Computer Vision course, or it's PyFLE and Justin Johnson course right now. CS231N GitHub.io. You can check it out. It's pretty cool. They have like put a lot of content out there. I'm referring to Adam Gateke's blog. Adam Gatke actually writes really cool blogs. Then I'm referring to the Keras repository of examples too. The code what I'm using without explanation is actually there in Keras repository. So that is what I'm doing. Okay. So Keras does let you choose. I mean, how many of you were there in the last session? I used like a meme there. It said like, yeah, this is what people think we do, and this is what actually we do, right? That is exactly what we do. If you look at it, it's Python code. Deep learning, lot of deep learning is Python code. It does get converted into something in the backend, but yeah, when we write it as Python code. So here as I said, supports multiple backends. TensorFlow, it supports TensorFlow, or it runs on top of TensorFlow, Theano, CNTK, and a lot of other frameworks, right? So we are going to use TensorFlow here, just to make life a little simpler. You don't need to deal with installing other packages. Okay. So the way you execute something in IPython notebook is Shift Enter. So I'm just importing things here. Just to make life a little simpler. You don't need to deal with installing other packages. Okay. So the way you execute something in IPython notebook is Shift Enter. So I'm just importing things here. All right. Let me actually clear the restart. Takes a little bit of time for import. Not sure why usually import is happening like this for the new version of Keras 2.1. Then I'm actually getting the dataset loaded. So Keras does have like a lot of these small toy datasets. There is a library which helps you in Keras. There's a library which helps you to load all the datasets easily, so you don't need to worry about it. That's what I'm doing here. It's returning a tuple for me. The training dataset, the X-train, Y is your target that you're trying to predict or train your model on. The other is like the validation, X-test and Y-test. X-test and Y-test. Okay. So I'm imported it. Now I want to actually see how the data is, right? So I want to actually see how the data set is, right? So here I have what is that I'm really looking at. So these are the handwritten digits, right? So that's a 4, there's a 1. I don't know what that one is, probably 7 or a 1. 7, yeah. And there's 7, yeah. And there's a 9, right? So just randomly print it, just see how things are underneath. That's the way I build my models. I want to explore I want to feel the data. I call it feeling the data, but I actually want to see what's really going on underneath, right? You can try throwing stuff model at it, or a complex algorithm at it, but without even you understanding what's really going on, that's not going to help. So I really like to see what is there, query it, see what's going on. So this is one of those. So let's actually see how the data set is shaped, right? The X-train, it has 60,000 samples, okay, and it is 28 by 28. So when you look at it, it's nothing but when you look at it, it's 28 by 28 is this, right? Let's say 0 to 28. Be like this 0 here, right? 28 columns or 28 rows, right? And what the 60,000 means is there's so many images of that nature.
So Malai, one of these, the 4 itself is one of those 60,000 samples, right?
One of those 60,000 samples, yes. That's correct. Actually, let's print it and let's actually see that, right? I'm taking one of those, the number 1, x train of 0, right? And let's print it and see what's coming up. So 0 to 28, as I said, one sample. And again, here you have 0 to 28, right? So there are 60,000 samples of that nature. Okay? That is what you want to throw at. But this poses an interesting problem, which we'll see. So whenever we feed anything to machine learning algorithm, traditionally, right, vectors, that is what we feed. So ideally, what you would like to have is your sample, right, as rows, and your values as columns, right, features as columns, samples, features. That's the way it will be, right? So, but here we have a 3-dimension. Oh, it looks like a 3-dimension, but yeah, we have a 3-dimension. As the number of samples coming into the perspective, the 3D tensor, right? So if we have to use the fully connected neural network, the one what we talked about the last session, right? A simple example where we built a model from scratch using NumPy for a synthetic data set, 0 and 1, like, where it learned. So we actually had a number of samples and rows there, right? So we need to like flatten things out and push it in. That's the way a feedforward neural network would work. So I'm going to build a feedforward neural network here. I think I told this joke in the last session too. So looks like I'm getting old or my jokes are not getting new. Something is happening. But anyway, so I'm importing the data set. I'm importing few layers in Keras. There is a sequential is a graph. Okay. Then there's dense dropout. Utils. There's a util function in Keras which takes care of most of the stuff what we really need. So I'm going to use a seed here. Seed will help me to recreate the same results again and again. Otherwise, if you want to like without using a seed, you may end up with a different result that try to run the same code later, right? So that is what it helps me to do. So now what I'm doing here is again, like I'm trying to see what's the shape, simple. But what I have to do now to feed it into a feedforward neural network, I need to flatten this, right? Instead of it being a 28 by 28, what I'll do, I'll flatten it. So 28 into 28, 784, right? Anyway, I'm cheating, I know the number. So, and your sample, 60,000, right? That's the way I'm dealing with right now. So I'm flattening it out. So I can feed it to a feedforward dense layer, right? In Keras, feedforward is dense. It's called dense layer. Everything in Keras is layers. The way you deal with it, everything is called layers there. And in most deep learning algorithms or framework, that's the way it's called. So here, what I'm trying to do is do something called one-hot encoding. What does it really mean is if I have like 2 values or 3 values, is it going to range? If you look at the weather condition, let's say sunny, rainy, and cloudy, right? So I'm going to make that as a one-hot encoder. It's n-1 usually, but for scientists say let's use this. So whenever the value for this particular, so these are the valid values in a single column. Let's assume that, right? So whenever only those values are coming, it will be set to like something like this. So that's one-hot encoding. Okay, so it spreads it out. So you do one-hot encoding your outputs. Now what I'm doing is actually initializing a graph. If you look underneath any deep learning framework, it is a directed acyclic graph. PyTorch is a little different. It uses a dynamic graph, but other frameworks, PyTorch and Chainer actually uses dynamic graphs. But rest of the deep learning frameworks, what they use is they use a static graph, right? You build it during compile time. It's called symbolic programming. You build it during compile time, like and then you execute it. it helps to do the back propagation better. That's the learning for deep learning algorithms. So I initialize my model here as a sequential graph. Keras does support to sequential and functional. So it does support too. So the next one, what I'm going to do is I'm going to initialize a dense layer. I'll try to explain what parameters the dense layer takes. Dense layer takes actually a few parameters. I have an output dimension. The output dimension of the dense layer, in this case, I'm going to give 512 as an input. Then what I'm doing is I have a input dimension, the number of pixels, 784, the one what we flatten, right? Initialization, I'm going to, how do you want to initialize the weights when it starts, right? You randomize it, but there are different ways how you can do it. Init is one of those functions, normal. Activation function, I'm using something called ReLU. There are a lot of activation functions. There are sigmoid, there is tannage, there is ReLU, there is leaky ReLU. Is there anything else I'm missing, Jeff? Yeah, the common ones, right? Yeah. Any questions on the phone? No. Okay. So that's what the activation functions are. Then you have an input dimension, which are giving us an input, which I talked about, right? And it's actually a good practice to name your layer. I'll explain why you have to do that a little later. It actually helps you to understand what's going on, like what layer is connected to what. So that's my layer one, right? I've added my layer one to that. The next layer, I'm directly going to the classification side of things. So the first layer I had like 512 neurons. The next one I'm going to connect it to the number of classes, right? The number of classes is how many classes are we trying to predict here in case of handwritten digits? Okay, yeah, so 0 to 9, right? So it's 10 classes. Okay, so we are trying to predict 10 classes here. So I have 10 classes here. The initialization is normal and the activation function is softmax. So softmax makes everything look like a probability. That's what softmax does. So if you need more details on softmax, you can Google for it, or I've written a blog on how you actually go about constructing a softmax. I have number implementation for it in my personal blog. You can check it out, Malaikannan.io. Okay, so we do that. Then what do we do? So I've added my second layer. Right? Now the Keras model needs to be compiled. So that's what I'm doing. You need a loss function for any model what you build. That's when it really knows whether it has to maximize or minimize something and how you actually train, right? So there are different loss functions. In this case, I'm going to use categorical cross entropy as a loss function. Again, I have like a blog on that and how it really works underneath, along with the code explaining step by step to go through it. Check it out. And the optimizer, there are different optimizers available on how you're going to update the weights, how soon you're going to update the weights, and all those things. There is RMS prop, there's Adam, then there is SGD, stochastic gradient descent. Am I missing something? Momentum and Nestor momentum, right? Nestor momentum. There's like few others of that nature. Yeah. So here in this case, I'm going to use Adam. Okay. So I compile my model. This one. Just reinitializing, just making sure that I didn't have anything old that was there. Yeah, it's training now. So the best part about this particular data set is it can actually train on a CPU. Right now it's training on my Mac here. You can see the validation accuracy is coming up with 0.9554 or whatever, right? So don't get spoiled by looking at this one. It's fairly accurate for a first get model to be trained on a first iteration. Usually it doesn't happen this way. You have to like go through a couple of iterations or a couple of epochs to actually come to a decent level of accuracy. So I'm just running 10 epochs here right now for fit. So it's probably gonna get done in another couple of minutes or even faster than that.
So in this case, you train your model on the training set and then
use the validation.
Accuracy is from the test set.
Yes, that's right. So yeah, the final accuracy is what, like 0.98, validation accuracy is 98%. We call it that way, right? That's fairly accurate for a model. Okay. So now let's look at. So yeah, we trained it with the feedforward fully connected neural network, right? Yeah, it works. So why do we even need a convolution neural network? Oh, okay, I'll go through it. So let's take this as an example, right? Here, I have an 8. Okay, I'm going to feed this to a model. It's going to say, yeah, 100% this is an 8, right? And it's going to say 100% this is not an 8. So what do? We flatten things out. Remember? So it's going to catch up to us in a little bit whenever you flatten things out. Let's actually look at the same thing. We know this is an 8, right? It's in a different corner of a image. We know that is an 8, but the model doesn't know that is an 8. So it doesn't know what it is, right? It doesn't know what it is either. Different corners. So a fully connected neural network doesn't understand that a moving object in a picture doesn't make it different, right? So the convolution neural nets, you need to give something. It helps you to give something called as translational invariance. That is the key. So that's number one reason why you want to use a convolution neural net. The second thing is, if you use a fully connected neural network, you will have the amount of computation what you have to do. The weights would be like humongous. So if you want to port it over, yeah, I'm training my model, fine. I have like good amount of GPUs to train my model. But when I want to actually take it and run it in a machine for inference later, right? Let's say, like, I don't know whether you guys saw the Google I/O, 2% talking to each other right there, right? In different languages. It was translating for them. It helps them to communicate better. If you want to do something of that nature on a phone or something of that sort, right, you can't have that in computations. It's going to be extremely expensive to do. So you need to decrease the computation. So convolution neural nets help you to do that. So it uses something called as weight sharing. So these are the two reasons why you go towards CNN for images. Okay.
Convolutions help with something like rotation.
It will. So the way it works is it achieves that in 4 steps. It's a 4-step process, right? First thing what it does is, again, I got this image from Adam Gately's blog. So the way it works is it breaks the image into overlapping image types, right? Image tiles, okay? Then it passes a sliding window across these image types, right? Think of it like your viewfinder or whatever, like this, as big it is, that is what it really does. This thing can be like a 3x, they call it kernel, it can be a 3x3, 5x5, 7x7, or depending on the images what you work with. For in our case, right, if you go after like the biopsy, I hope I'm saying that right, for cancer images, right, biopsy, yes. So biopsy images, there the viewpoint can be little even bigger. The kernel size can be even bigger. I've seen papers where they use like even bigger kernel size rather than 7x7. So that is what it does, right? So it divides the image into overlapping image tiles and then it passes the sliding window across. So step 1. So what does it do on step 2, right? It takes this image tile and feeds into a smaller neural network. I don't care about the entire 512 size neural network. I don't care about it right now. All I'm going to do is take that small image, feed it into a a separate small neural network. Okay? The entire image is fed into one neural network. In this approach, we will so weights and gradients, right? As I said, it's weight sharing. Weights and gradients will be shared across every single tile in the image. Okay? So this is the way it works. There's an input tile, there's a small network, and there's an output tile. So what does it do? It saves the results from each tile into a new array, right? So these are my input tiles. Then I have a rather small neural network, a shared weights what I'm calculating, and this is my output array what I'm coming up with. So whatever position that I had my small neural network calculate, I'll put that output array in the same position. So the grid arrangement, right? So I don't lose things. Okay. So I do that, and then what is the next step? It's something called as pooling, max pooling. I think so we talked about it. So it works this way, right? So you take a picture or something. Where does the eye go immediately? You tend to get attracted to the brightest things that is out there. That is where most of the information is. So here, let's say if I have like a 2x2 grid, right? I have a 2x2 grid. So I have a value of, let's say, pixel values, right? I have a value of 10 here, I have a value of 20 here, I have a value of 8 here, and I have a value of 200 here. Okay? So what max pooling does is it takes this value. So that contains maximum amount of information. The way deep learning algorithm works on it, that's actually a theoretical proof that was published week and a half, 2 weeks back. The way it works is it's called information bottleneck. Okay? This has been thrown around as an idea for some time. Somebody from Israel actually published a paper on it. I'll send that over to you. The way it works is you keep reducing the amount of information what it can have, right? In a step-by-step process. You're forcing the network to actually choose only the important ones. And max pooling actually helps you to achieve it. There are newer networks, newer architecture that are coming out that actually got away with max pooling completely. It's like a cat on the wall, right? People go both sides. Some people don't even like pooling operations. Some people like pooling operations. There are newer networks like RCNNs and stuff. They have got rid of pooling completely, and they are going towards a different approach altogether, one-by-one convolutions. So that seems to be working fairly well too on some of the research papers. But anyway, that is the idea for max pool. It takes the largest or brightest out there and builds this max pooled array. Okay. Now, what happens is now I'm going to import few other layers that I'm going to use I'm going to write a code here. I'm going to import few other layers that I'm going to use. So I'm going to use lens, I'm going to use dropout, which we used before, activation, there's a flatten, which I use, and then con 2D, max pooling 2D operations, all right? And as usual, I'm not going to write all the 1 coding myself, I'm going to use Keras utility. So this may not be applicable anymore since Theano is going out of support. So if people are still using it, if you want to download it now and set the default deep learning framework back to Theano, since it's very, very hard to install, you can do it, but it's extremely hard to install TensorFlow on Windows. Okay. So, so if you are using Theano in that case, you want to worry about the dimension ordering for images. That's different between TensorFlow and Theano. Theano uses number of sample, channels, height, and width for an image. TensorFlow uses sample, height, width, and channels. So if you train your model, take this data and or take this code and try to run it, but using Theano, is make sure that is accurate. Otherwise, the model is not going to converge. Okay. It's very small thing. What myself, I have been bumped into a few times where you don't check it and you end up spending so much time why the model is not converging and stuff like that. You try every aspect and then go and look at it. So make that as your first step. So I'm setting the dimension ordering to TensorFlow. Now here, right, same thing. I have to choose few things here. I'm going to choose a number of filters, how many layers I'm going to get after I push my model through this particular Con2D operation. So that's called by number of filters. How many layers I'm going to stack one over the other. The pool size, that is this one, right? Max pooling 2 by 2 or whatever. That's the pool size. The kernel size is the viewpoint or viewfinder kind of a thing in a camera, right? So that here in this case, I'm going to use a 3 by 3. Again, you can play with it in however you really want to use it. Okay. So I have a batch size, classes, epochs, image rows, image columns, and all those things, right? So I've done that. I'm going to load it again just to make sure. So I've loaded it. So you have to watch this one out, right? When we looked at that size of the image, it was 28 by 28. It didn't have a channel information. Right? It's grayscale, so it didn't have a channel information. But traditionally, if you look at an image, usually it has an RGB, right? Red, green, and blue. So you have 3 channels already there. So instead of it being like this, it will be a 4D tensor. That's the way it will be. Okay, so this 3, and then you'll have repeating stuff. That's the way it will be from a tensor perspective. Right here, we don't have it. So what I need to do is I need to reshape it so I can actually send it through a Con2D operation. So that's what I'm doing. I'm reshaping it here. I've reshaped it. We look at it, now it's 60,028 by 28 by 1 rather than in this previous case, what did we have? $60,028 by 28. In fact, we flattened that one out to 60,000 by 784 when we actually fed it into Feedforward No Network. Is this clear?
Mm-hmm.
Yeah. Any questions?
So the NB filter is the number of small neural networks?
No, layers.
Okay.
Layers.
How many times it will?
Yeah, how many channels you want to get after. Okay, so I'm in train shape. Okay, so let me show you this one too, just to make sure that you got it. So I'm doing one-hot encoding. I'm making sure things are normalized. Got it? So now I'm going to do my model, right? I have a convolution neural net model. Let's actually walk through that. As I said, everything's a graph. You keep adding, connecting nodes, different layers to different graph, sequential. So that's my graph. I'm initializing it. So I'm going to add a Con2D operation here. So I have given like the number of filters, 32. Remember, that's what the output of it is going to be. The kernel size is like 3 by 3, right? That's going to be my kernel size. Bottom model valid. I'll dethrone a little bit on that. What does it really mean? And the input shape. How it's going to be, right? The number of rows, columns, and stuff. Okay, so that's my first level, right? So you added your convolution 2D. I mean, you can put how many ever fancy stuff on it, but without an activation function, you're not going to learn the nonlinear pattern. Okay, so the activation function is the one which actually helps you to learn that. Now you're putting an activation function there. In this case, I'm going to use ReLU. That seems to be the most common one people are using nowadays, ReLU or leaky ReLU. That's the most common one. TANH or sigmoid have fallen out of favor. And there are papers which are coming out with that, but not much. I haven't seen much around. Let's put it that way, it's not cool anymore to use it. So then I'm going to put a max pooling 2D operation. After Con2D, I'm going to put a max pooling 2D operation. Then I'm going to put a dropout. After that, dropout, and Jeff smiles for a reason. In fact, my previous stint at Saama, I used to bug Jeff for that particular paper to understand the math behind it. It's a fairly fascinating paper. The idea is to randomly drop connections, right? It's like me preparing for an exam, let's put it that way. I can prepare that entire book. I can try to understand what that book is, or I can try to memorize that entire book. Okay. If you memorize that entire book, if even some application-oriented question that comes out in your exam, you'll not be able to answer it. You don't want the neural network or the deep learning model to actually memorize the entire data. you want it to learn the pattern of the data, right? To make sure it learns the pattern of the data, what you do is randomly drop, so like turning the pages off, right? So making sure that you don't memorize it. Even if you memorize it, it's not going to be of much help. So that's what dropout does. Then flattens the entire thing out after you do that. And I'm going to do a dense 128. You usually have a fully connected neural network. You tap onto after. So I said before, if you actually look at it, it will look like a pyramid, right? With the softmax on top. That's how most of the convolution neural net architecture looks like, some form of the other. Not the inception ones and stuff like that. You have like things branching out, coming back and connecting and all those things. But that's the principle behind it. It's information bottleneck, right? You have a lot of information here. You keep reducing it to a point where you get it to a point where you make it choose only the important stuff, and then you put a softmax on top to classify it. Okay. So I'm tagging a dense 128 on it, and then I'm going to put a activation function of ReLU again, and then I'm going to put another dense layer for the number of classes what I'm trying to classify with an activation of softmax. So we talked about loss function before. Here again, I'm going to use categorical cross entropy as a loss function. Optimizer is Adam, and the metrics is accuracy. Right? That's actually. Okay, so I executed it. Let's actually train it. Do you want to train it? No, yes?
Yes.
I think there's a question.
Okay.
So he asked when to use sigmoid versus ReLU.
When to use sigmoid versus ReLU? Again, sigmoid doesn't learn well on a lot of new stuff. That's what they found out. Again, it's empirical in nature. I don't have a mathematical explanation for it on when to use it and not to use. But the empirical results, right? They've run different models, trained different model on different data sets, and the way they have come up with this, like so far from what I've seen, sigmoid, they don't use sigmoid anymore. Maybe if you have any background on it.
I mean, from a mathematical perspective, I can't give you more than that. But yeah, from an empirical perspective, ReLU has proven very effective in a lot of newer networks.
So what they say about sigmoid function is that the sigmoid function has got a very, the gradient, right? It's very difficult to learn.
Okay.
So what happens is that when you have these really dense connected networks, the gradients are more and more difficult to learn, and the function takes very long to go through the gradient.
Yeah.
Whereas ReLU and tanh, these functions, they tend to get your gradient tends to be a lot steeper, so that you are able to learn the function a lot faster. That's the intuition that was provided during some of the things that I read about ReLU and sigmoid.
Good explanation. Yeah. So how many efforts do you guys want to put? The number? 100?
No, don't do that.
Let's do 100.
When I ran it on my machine, one ePocket, maybe took a couple minutes. So
Yeah.
I think 100 might be pushing it.
The battery would die. Usually that's what happens, right? You see this noise coming out from the fans on the side, and somebody's
We'll see the result in the next TechTalk.
Yeah. Okay. So now you guys understand why why the reason why I want to take you through a feedforward to convolution is to understand that why CNN or convolution neural networks actually works well for images, right? So translation invariance, number of weights what you have to deal with, and all those things. It learns fairly fast compared to a feedforward. Not in this case, but yeah. But you already start seeing numbers coming out, right? 0.9736 and all those things. So it's a good level of accuracy. It's going to run for another 10 epochs, right? Okay. So the reason why I used a MNIST data set, right? It's all pre-processed. In our case, right? I didn't want to go through the entire time, trying to how to teach how to pre-process an image, how do you do that, and load it, all those things. But if you want to learn it, I have a reference here, a link here. It's actually a fairly good information. It explains how you go about it, how do you actually use OpenCV or something, or Matplotlib to clean it, like load it, rotate it, augment it, and like do stuff. So that is one thing. The other stuff, what I do, it's not working. I have installed model.is. I actually like to visualize my architecture. What is connected to what? How my layers are connected, right? So that actually helps me to debug. Let me actually pull up from GitHub. I don't know whether it's pushing over. Yeah, ideally that's the way it should look. Okay, so when you visualize it, it becomes a lot easier, right? Now I know what is my input, what I'm getting out of it, shapes. Most of the time, if you like build models using images or anything in deep learning, you will get the shape error. You're gonna run into it, right? If you're gonna run into it, this is the tool what I actually use for debugging. I need to understand how the shapes are connected. This network is a fairly simple one, right? So I know what I'm doing. But if you're going for a complicated network, ImageNet, the previous ImageNet, ResNet architecture 150, it had like 150 layers. Good luck trying to figure out where the shape error is coming from, right? Things like that, we're going to make it complicated. So this is a fairly good tool to actually understand why things work, okay? Or like how things are connected. So Con2D input one, you have like input. So here my input is none, which is the number of samples, right? 28 by 1. The output one I'm going to get is the input layer, right? So 28 by 1. So when you do a Con2D, actual Con2D operation here, you see 28 by 1, and the output what you're going to get is 26 by 32. So and remember the question what you asked, Paul? Filters.
Yes.
Yeah, that's the output volume you're getting. Okay. So now I'm going to pass for the activation function does not change the shape of your tensor. Okay. So that's going to be remain the same. When you look at max pooling, see the size gets decreased. It works only on the spatial or temporal. I'm trying to find the right term to explain it. Sorry, I'm not a mathematician. So. So anyway, it doesn't work. Let me put it this way, right? It doesn't work on volumes. Okay, it doesn't. Max pooling does not touch the volume side of things. The 32, it doesn't touch that. It doesn't decrease it. It only works on the row and column, right? So 26 by 26 went into 13 by 13 by 32. Okay? Dropout does not change your tensor size, but flatten does. 13 by 32, right? The output is 5408. When you multiply that, that is what you're going to get, the flattened vector, right? So that is what you're going to give to dense as an input. The dense layer, what I used, 5408, and you're going to get like 128 as an output, since I've used 128 neurons in it, right? This activation again does not change your tensor size. But this last dense layer does change. So that's where you add a number of classes to it. So none 128 and none 10, right? So the last activation is softmax, so does not change your size. But it helps you to go through this entire, it helps you to understand how your model is working. Try to visualize it. If you're building something, like try to visualize it. That's the best way to actually debug. Understand how things are going. Any questions so far? Fairly silent audience today. So a couple of other tips is, I mean, if you want to learn more about it, this session is meant to be like a primer for you to start with. But if you want to learn more about it, try to take like the CS231N from Stanford. That gives you like a really, really good understanding of how CNN works. In fact, try to look at the older lectures from Andre Karpathy. He is a really good teacher. I mean, like, you can explain things in a fairly, you can explain fairly well, right? Along with the math and without the math too. So that's his strength. Okay. And if you want to understand it even further, I would actually suggest you to actually write. Don't use Keras, TensorFlow, and all those things. Make your life a lot simpler since I've already built these primitives or Con2D, Con1D, or whatever. Max pooling. If you don't want to deal with it, right? Write things from scratch. That's the best way to get your understanding. Whatever language you're comfortable with. If you want to do it in JavaScript, do it in JavaScript. Android Kakati actually has a JavaScript library for it. So it's very interesting to do that. It gets, I mean, you understand things a lot better. Okay? So that is one. The other thing is, yeah, so you don't need to actually come up with your own architecture most of the times. That's the truth about when if you're solving some problem which is like extremely hard and all those things, yeah, you have to try it. But there's a concept called transfer learning. It works most of the times. So they have trained a model on something else, let's say to identify a cat and a dog, but they have like trained it. The best thing about deep learning community is it's really open. All those things have an Apache 2.0 license. You can download it, download the architecture, download the weights, pop the last 2 layers, remove the last 2 layers, just fine tune for that alone. Even if you have small amount of images to actually train your model, it will train well. You can actually get a decent level of accuracy on it. So use transfer learning. If I'm going to say transfer learning in Android Karpathi's words, I'll say like don't be a hero. Don't try to build your own architecture from scratch. It's going to take a lot of time for you to get an output. So do this, get an output, and then in parallel run your other model too. That way you have something to show or bounce things off, stuff like that. So that is one. Yeah, again, take a problem and work on it. That's what I would suggest.
So just one thing, I mean, I'm talking from a layman's perspective. Can you cite 2 or 3 examples, in an environment, be it in any of the customer side, right, where image processing can be used, or where we can sell this as an idea, or there can be a potential example where they might be doing something not using CNN or other things, maybe some other ways. Are there those 2 or 3 examples that you can share, in your practical examples?
Sure. So let's say OCR is a classic example for CNN, right? There are different ways to do OCRs. Tesseract is pretty good. Like you can get like decent output. But you want to improve it even further, you can actually use CNN for OCR. There are papers which have come out like use like really good results on that. That is one, right? Anytime you deal with images, this is the only option that is out there. I don't see anything else that is out there that helps you to solve it better. Since you have to learn so many business rules for you to do that. Even for actually grouping images together, let's put it that way, right? Right now you look at a classification problem. In fact, like one of the next topic, what I'm going to do is on similar lines. I'm actually writing a blog on it more for my personal side. How to buy a home with a kitchen you like with deep learning, right? My wife likes kitchen to be in a very specific way, right? And if you look at it and all those things, try to look at it, and she's going to say no for a lot of those things. So she's written a crawler to get the data and building a model to actually help you to categorize things together. And we know what she likes, right? What kind of kitchen she likes. So it's a pure cosine similarity kind of a thing. So that's one of the talks we are going to do later. But yeah, it can help you to group images together. So even if you have like cancer images or whatever, right? If you want to group things together, like what is related to what, it works really well.
So OCR is one example where you can use Tesseract, right? But I think you said that you can also use deep learning.
Yes.
So when would you use the Tesseract versus the deep learning?
Good question, right? So Tesseract, from what I've seen, is it will work really well with like when you have a printed document, right, which is scanned or whatever, it works really well. When it's a handwritten document, Tesseract fails. In that case, it's better to actually use CNN. CNN is meant for that. So yeah. In fact, the example for handwritten digits, what you saw here, if your mail goes to a wrong place, right, that's probably the reason. It's used by, or at least it used to be used by USPS to send things or understand what is the zip code that the mail is supposed to go and like sort it. So yeah.
But if you're looking for other like, business applications, for instance, he already mentioned, biopsy data. If you have image of tissue, you could be wanting to say, identify cancerous tissue in there, and that's actually a very difficult task. You know, as a human, even the professionals trained in how to do it will defer to one another if they don't know necessarily. So that's an interesting thing that
These are
research.
tasks, like facial recognition, product recognition. When you have a gathering of your customers and there are walking around with their products, you could have facial recognition, product recognition, get a lot of information about retail surroundings. I don't know.
It's very similar to in Google, right? In Google Photos, you tag a person, but then it understands that even if it is something different, it knows that this person is the same. Okay.
It is.
Yeah.
So all those image processing is based on CNN. That is the math, or this is the one which just a magic under the hood. So if you how many of you have actually bought an iPhone X already? Probably a few tried but haven't bought it.
8, 10 is due in November. Yeah, not so.
Okay. Not out. So the Face ID, that thing, right? Yes. Again, Samsung people are gonna say that it had it for a long time, yes, right? But Face ID, that's facial. Right? That's actually a CNN model. It's called FaceNet, or one variation of that. It works fairly well. There are different aspects, different stuff like that. There are a lot of use cases. Anything that's image related, right? I'm not able to come up with a good one from a life sciences perspective.
This was a good example.
Yeah,
that's what I wanted to understand. Yeah, I think
that is one. There are other.
Even when you said fax processing, I think that's what comes to my mind. If it is handwritten versus, I think those are the examples where I think in the clinical space, as well as in the MedAffairs space, they rely a lot because they have a lot of facts that come in, and then there is manual work in recognizing those things.
So if there's no other questions, I think we are probably right on time to finish the session.
You didn't show us the accuracy.
Oh no. And you are 9853. 98%. Put it that way. What is the feedforward?
Does your test set now contain translated images and rotated images?
Yeah, I augmented. Yes. There's an augmentation routine out of Keras. Works fairly well. It rotates, like it does a lot of other shifting. Okay. So thank you for attending. If you have questions and stuff like that, let me know. And the code for this is available in my GitHub. The email was sent out already, but I'll send a follow-up email with the link. I'm there.
Yeah, just wanted to actually ask a question. See, we listened to the saw this entire session. It was very, I think, illuminating. But I wanted to ask you, if we are looking at not image classification problem, because on the safety team, there is no direct image classification problem.
Yeah.
Is there a parallel thing? On the text side of things, can you give a couple of use cases where feed-forward neural networks or CNN can be used?
Oh, yes. So, Saumya, there's a blog which I wrote in Saama, right? If you take a look at it, okay? So there, I've actually pivoted towards using CNN Con 1D for text NLP, all right? So that was more for generating and embedding, but you can actually dig it even further, use for parts of speech tagging and stuff. So even safety, right? Safety, if you have like a social media text or whatever, you can look at it, it's an NLP problem, right? Natural language processing problem. But that can be further divided into something like an entity extraction, right? I need to extract the drug names, I need to extract the event names, whatever they are telling in that particular text. right? And any dates or whatever. So that is an entity extraction problem. Okay. So so that is actually a deep learning thing. I mean, like, no, you can solve it. Yeah, you can solve it with parsers, but you can't solve it effectively. But if you want to solve it well, you probably have to use deep learning for it. So convolution 1D can be used. Con 1D can be used for it. Okay. A different flavor of CNN, right? Then you have a relationship extraction problem, right? You have to go through the tree, find what words are related to what, like, in that context, and identify and extract it. Let's say this particular drug is reporting this particular event. They would have said totally different thing in a text, right? If they write like a paragraph, you don't know whether it's that particular event. What they are saying is that is related to the drug in that thing. So if you want to extract that, that is a deep learning thing too. Again, classic NLUs, right? Large language understanding engine. So all these things are going towards deep learning per se. That's where you can solve it effectively on the safety side of things. So.
Okay. Thanks, Malay.
Yeah, sorry, this was more on the image processing side of things, Soumya. We'll have another session on the NLP side of things. So.
Okay.
Yeah. Thanks, guys. Thank you.
Thanks, Malay.